Number 1 asks us which of the following is true, and it's asking us about sine and cosine. So let's remember the acronym that you can use for remembering sine, cosine, and tangent. So it's SO, CA, TOA, meaning that sine is the opposite side over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. Remember, it matters which angle we're using. So in this case, we're looking, for the first one at least, we're looking at angle A, and sine means we want the side opposite of A, which is the 6, over the hypotenuse, which in this whole problem will be 10. So sine of A is equal to 6 over 10. That's true. So the first one is true. That means the rest of them are going to be false. We can take a look at them though. So cosine of A would need to be the adjacent. So adjacent or next to angle A is the 8. So this is the adjacent side. So cosine of A should be 8 over the hypotenuse 10. And then in right triangle trig, we don't do trig of the 90-degree angle. So we can't do sine, cosine, tangent of 90 using right triangle trig, because the opposite and the hypotenuse would end up kind of being the same side. So certainly these ones are false. Number 2, here's triangle ABC. Express the length of AB in using sine or cosine. So let's take a look at AB. So here's AB. So if we're doing sine or cosine of theta, we know that this side right here is adjacent to theta, and then AC is the hypotenuse. And so the trig function that puts together the adjacent and the hypotenuse is cosine. So CAH, adjacent over hypotenuse. So the cosine of theta is going to equal the adjacent side, AB, over the hypotenuse, which is 1. And anything divided by itself is just itself. So AB over 1 is just AB. So AB is actually equal to cosine of theta. Then looking at BC, so here's BC compared to theta, that is the opposite side, right? Directly across from it. So this is the opposite. And again, we still have the hypotenuse at 1. So opposite and hypotenuse is our sine function. So sine of theta is going to equal the opposite side, BC, over the hypotenuse, which is 1. So sine of theta is equal to BC, or BC is equal to sine of theta. So AB was cosine, BC was sine of theta. Number 3, these two triangles are similar to each other. So what is the length of segment DE and what is the length of segment EF? So DE is here. It's comparable to AB. And then the side that they give us both measurements of, right, is this hypotenuse. And so if these are similar, they have the same scale factor. That means whatever I did to one side, multiplication or division, I do to the others to figure out their length. So here we go from 13 to 1. So this is just dividing by 13. So then I'm going to do that to each of these other sides to get their corresponding sides. So DE is going to equal 12 divided by 13, divided by that scale factor. So we would just divide 12 by 13 to get this part. And then when we go to do EF, a very similar thing, right? So this one goes with BC. So these are similar. So we're going to take BC's measurement of 5, divide it by 13 to get that side. So EF is going to equal BC divided by 13. And then explain why we know that the length of DC is cosine of D and the length of EF is sine of D. So for, so now we're looking at this little triangle here, right, for DE. So, whoops. So the cosine of D, so if we're looking at angle D, the cosine is adjacent, which is side DE, over hypotenuse, which is side DF. And we know that DF is equal to 1. So cosine of D is just going to be equal to DE divided by 1, or just DE. So then we know that DE is equal to the cosine of D. And a very similar thing for EF, right? So if we do sine of D, sine of D is equal to the opposite, which is EF, over the hypotenuse, which is DF. And we know that side DF is equal to 1. So sine of D is going to equal EF. Number 4, here's a triangle. Find the sine, cosine, and tangent for angle A. So I'll just write SOHCAHTOA up here again to remind us. When we go to find the sine, so the sine of A, I guess I'm doing this one first. The sine of A is equal to the opposite side over the hypotenuse. And the opposite of angle A is 2. And then we're going to need this hypotenuse. So let's solve for the hypotenuse. So we have a right triangle. So then the hypotenuse, we can do Pythagorean theorem. So we can just do the hypotenuse squared is equal to the 2 legs squared and added together. So 2 squared plus 6 squared. 6 squared is 36. 2 squared is 4. 36 plus 4 is 40. So then we would do the square root of both sides, and we get that the hypotenuse is square root of 40. So the sine is going to be opposite 2 over hypotenuse square root 40. Then cosine is going to be the adjacent over the hypotenuse. So cosine is the adjacent side over the hypotenuse. So the adjacent side to this angle A is the 6 over the hypotenuse is still square root 40. And then finally the tangent. So tangent of A is going to equal the opposite side over the adjacent side. So opposite of angle A is that 2. Adjacent to angle A is the 6. So the tangent is going to be 2 over 6. Number 5, sketch and label a right triangle ABC so that tangent of A is equal to 2. So remember that tangent is that TOA part, right? So the tangent of angle A, so tangent is equal to the opposite side over the adjacent side. So the opposite of angle A divided by the adjacent has to equal 2. So we could say that it's going to be 2 over 1, right? So the opposite could be 2 and the adjacent could be 1. So I'm just going to put angle A right here. And so I'm going to open this up so that the opposite of angle A is going to be 2. So this is 1, 2 here. And the adjacent is 1. So I get the adjacent side and then the opposite side. So opposite side is 2, adjacent side is 1. Here's angle A, so I'll call this B and C. So then we have tangent of A equals 2 over 1. And we have a right triangle here because we have horizontal and vertical line. Number 6, the point 1, 4 lies on a circle centered at 0, 0. Name at least one point in each quadrant that lies on the circle. So let's just draw out the coordinate plane here. So we know that this circle is centered at 0, 0. And we know that the point 1, 4, so 1, 4 lies on the circle. Name at least one point in every quadrant. And so we just have to make sure that the radius stays the same. So basically the legs of this triangle can stay the same. So this 1 and 4, because then 1 squared plus 4 squared would be giving us that radius, right? So as long as we kind of keep the same two legs, that's going to work out. So 1 and 4. So we could go in this quadrant and name the reflected point here. We could name this one. That would just be -1, 4. You could do the similar thing here. Okay, so a 1 and a 4 into this quadrant would be -1, -4 in the third quadrant. And then a similar one here, 1, 4, but this would be 1, -4 to send us to the fourth quadrant. Another thing we could do is just kind of flip-flop the 4 and the 1. So we could do a 4 with a 1 y value, because that's still going to be a 4 squared and a 1 squared, right? So then this ordered pair would be the point 4, 1. And then we could do that in each quadrant. So we could go 4, 1 this way, which would be -4, 1. We could go 4, 1 this way, which would be a -4, -1 movement. We could go 4, 1 this way, which would be +4, -1. And all of those would end up being, you can kind of see the circle forming there.